objects, and fully convolutional networks were introduced as a powerful method to do that. And we propose to use that same nets for text segmentation. So we train one of these FCNs with Coco text, where we have ground truth text mask to find the pixels in an image that contain text, right? So this network was outputting level the input image, and those maps turned out to be pretty accurate, right? They were detecting different kind of text, and we found that they were detecting that this net was detecting text of different shapes, different rotations, and it was even detecting text written in alphabets where that the training data didn't contain. And researching on that, we find that it was also detecting as text hieroglyphics or other kind of textures that have a similar structure as text does, right? And that's not that strange. Actually, humans, we do a similar thing to recognize text. So for instance, we recognize as text alphabets, scripts that we might not understand, but we can still imagine those are text, right? So at the end, this text FCN is doing the same for detecting text in an image. So the state-of-the-art pipeline for text detection by that time consists on a object proposals method, actually text proposals specifically, followed by a word classifier. So the object proposals method proposed many regions in the image that were susceptible to contain text based on very simple cues, and then the object, the word recognizer, had to detect which ones of these regions actually were containing words. And one weakness of object proposals method is that they were proposing regions, even regions outside text areas, right? Let me see if this works. Yeah, even regions outside text areas. So what we propose here is to use the maps, the text probability map provided by the text FCN to suppress all these regions that were outside textual areas. And the result of that is that we end up with much less regions that have to be evaluated by the word recognizers. So this method results on better results when we analyzed with the word recognizer a limited number of proposals, and also on an efficiency boost of the whole algorithm when we analyze all the proposals, because we have to run the word recognizers for few of them. This was joint work with Dena Basazian, who also graduated from her PhD here last year in CBC, and it resulted in 2 publications with her. So yeah, also pleasure working with you, Dena. Okay, so let's go with the second research questions of this chapter, and that is, can we train a neural network to transfer text styles from text images, learning from a single image, I would add. So, a neural style model trains an image transformation network to transfer the style from a source content, to transfer the style from a source style image to a source content image, preserving the image content. What that means? That means that we want to generate an image that has the same content, which applied to text means the text transcription as the source content image, but with the style which applied to text means the shape of the letters, the colors, the kind of stroke it has of a source style image. And this works by training an image transformation network to generate an image that shares high-level features with the source content image and low and mid-level features with the source style image. So we train this network and we generate an image that has the source text style along all the image, and then we use the maps computed by the text FCN I was explaining before to transfer the style only to textual areas. So after this model, we propose an end-to-end model, which learns to do both tasks, style transfer and at once. So get the image that has been stylized by a pre-trained style transfer network, and using the Cocotex ground truth mask, which only to the textual areas network mean square error loss. And this end-to-end model ends up having similar results as the previous pipeline. And actually, we get quite good results from it. So here we have on the left the original images, on top the target text styles, and in the second and third column, the generated images. So as you see, we get that preserve the original text transcriptions, but with the new target styles. And we can think about many applications this can have, but we experiment with one, which is data augmentation. So basically, if we have a data set consisting on these original images, for which we have ground truth, we can add to that data set the new generated images, so the diversity in our training data. And that's what we do. We apply this to a standard text detection data set like IGDAR and COCO. And we standard text detection on the plain data sets and on the augmented data sets. And yeah, we see that the style transfer is an effective data augmentation method, and the text detector trained on those augmented data sets achieve a better text detection performance. We also apply this style transfer method to other types of text. For instance, here we apply it to matching print text. And you see that also the generated text preserves the transcriptions, and we get the styles that are in between the original style and the target style. And we also apply it to handwritten text, which seems a more difficult task. And still, we are getting text with the original text transcriptions and with a style that is pretty similar to the target style. We can also apply this in a cross-modal manner. So for instance, here we are stylizing matching with a syntext font, in this case this Fanta font. And that has several applications. For instance, we can do content augmentation. We can take an image with syntext and change the text content, the text transcription, but preserving the original style. So we only have qualitative results for that, but it can have many applications. So the conclusions of this last question is that first, we are able to transfer styles between syntax images learning from a single image because that net is learning textual texture features. And second, that the end-to-end method we propose for selective strand transfer can have many other applications in other domains. For instance, we could also apply it as a data augmentation method for object detection. And this was joint work with Ali, who is over there, also a PhD candidate in this lab. Also a pleasure working with you. And it resulted on also in a IGDAR publication last year. So that was the first chapter, and now let's go with the second one. So, in this second chapter, we are working with social media images with an associated text, which in this case, it's going to be an associated caption. And we are going to see how we can exploit that captions to learn visual features, using them as self-supervision and applying them to multimodal image retrieval. So we have tons of images with associated text. For instance, in Wikipedia we have articles that contain images, or in Instagram we have millions of photos with associated caption and tags, or the same in Twitter or in Flickr. And from that data we can learn which relations users establish between images and text in that different social networks. And at the end, here what we are learning is to learn the relations that users establish between visual concepts and text when the data has a synergetic semantic meaning, right? When the image and the text have a similar semantics. So in this chapter, we are going to work with these three data sets. The first one, Web Vision, is a data set containing Flickr and Google images with captions. The second one, InstaCities, is a data set we create made by Instagram images associated to English-speaking cities and their captions. And the second one, it's similar but containing Instagram images associated with Barcelona and their captions. So in this chapter, I'm going to use semantic text embedding models. And we are going to experiment with text representation models oriented to generate representations, to learn representation of long text, such as LDA or Talk2Vec, and also with word-level representation methods, such as Word2Vec, Glove, or fast text. And we are going to exploit a feature of these models, which is that they learn text representations with a semantic structure. For instance, operating with Word2Vec word representations, we can sum up the representations of mother and men and get the word representation of father. So they have these semantic structures, and you can perform arithmetics with them. So this is the methodology we propose. First, we are going to train these text representation models with the training text from social media, to ensure that we are learning representations for those specific social media words. And then we are going to train a CNN to embed images in that same text representation space by training it to embed an image in the same point as its associated caption it's embedded in. So at the end, we are going to end up with visual embedding and a textual embedding that can embed images and text respectively in the same space with semantic structure. So that allows us to apply it to image retrieval in a straightforward way. For instance, we can compute textual queries by combining word representations. We can sum up them, and then we point to a point in this embedding space and get the nearest images. And we can also apply that to multimodal image retrieval, where queries are composed by a word and an image. So this is going to be trained. This is trained with social media data. So we are learning visual features associated to any word we can imagine. So for instance, we have some results, some abstract queries, I would say, and we see the visual features that people in Instagram associate with them in Instagram, right? So we see that in Instagram, people associate the word happy with images of people smiling, or the word Monday with coffee. And we can perform complex queries. So for instance, we see that people associate food and fast with images of hamburgers, or food and healthy with images of salads. And this is particularly good retrieving images related to topics that are common in social media. Like for instance, the net can distinguish between hairstyles of men and hairstyles of women, or it can distinguish between along the world. And we can also perform multimodal queries. So for instance, here we're going to get an image similar to this sunset in the beach, or without the sunset. It also works doing that. So in here we conducted a performance comparison of the different text representation methods in image by text retrieval. And we see that level methods such as Word2Vec and Glove have superior results. And that's probably because of the data we are learning from, right? We are learning from images with associated captions, which in general are quite concise and even include hashtags associated to those images. And we publish those results in a NICCB workshop and also in a book chapter. So this method from learning from social media data has a huge potential. In here we see a TCNA plot which basically shows images where they are embedded in this join semantic space. So we can see, for instance, we have a cluster of food images, or we have a cluster of images related to beauty. And note that we can navigate all this space by using. So As I said, this can have many different applications because we can investigate with which visual concepts people relate in social media, which any word, right, any concept we can imagine. So they can have a lot of social and commercial applications. And here we research in one of them, and we are going to work with Instagram data related to Barcelona. So just training a word-to-vec model with the captions of this dataset, we see some applications it can have. For instance, if we inspect the words that people associate with healthy and restaurant, here we see some specific Barcelona restaurant names, right? So this can have an interest for the industry. And if similarly as we explained before, we train a visual embedding net to embed images in this word-to-vec space, for instance, that people associate the word breakfast with chocolate con churro images, or the word Poble Sec, which is a neighborhood of Barcelona, with these tapas images, which is a trendy thing to eat there. So I explained this application in Forum Touristic. Forum Touristic is a forum here in Barcelona to explain the latest technology and how they can be applied to the tourism industry. And I showed them how we could use these tools to analyze which concepts, both visual and textual concepts, people were associating with hotels, restaurants, or neighborhoods in Barcelona. And they seem pretty interested on it. So I was doing during this presentation, I realized that most of the data I was learning from was data from tourists. And I thought that I could also use these tools to analyze the tourism in a city. So what I did was to do a language separate analysis. And I did the same analysis in English and in local languages, Spanish and Catalan, assuming that English publications were from tourists and publications in local languages were from locals. Here we have a plot of the percentage of publications mentioning each one of the Barcelona neighborhoods. Yeah, of course, in more touristic neighborhoods, you get more publications in English. So what I did here is to compute a representation of the captions in the data set which show a similarity with each one of the neighborhoods in Barcelona. And then I train, similarly as before, a CNN to embed images in that space, in this case using a ranking loss. So, same before, we can retrieve which images people, in this case people speaking or posting in the different languages, associate with each one of the neighborhoods in Barcelona. So in here we see that here in red we see the results for English people. So we see that with Poble Sec they associate these images of tapas, but people speaking in local languages, Catalan and Spanish, they associate local gatherings or art galleries, right? So this is a tool that can be used to analyze the different behavior of different population groups in a city. And these experiments also resulted in a publication in an ECCB workshop. So then here, I want to show you how we can use this deep dream algorithm to analyze which kind of features this net is learning. Deep dream is written by Google, which hallucinates what a CNN sees in an image. So basically here we see this cloud's image, and if we apply a CNN trained with images on it, it starts hallucinating in animals in the clouds, because this ImageNet net has been trained with many animal images. And if we apply the same, but with the net trained with Instagram data from Barcelona, we see that it's learning patterns related to typical tourist attractions in Barcelona. So for instance, we see patterns related with the Montjuïc Fountain or patterns related with Sagrada Familia. And if we apply this to other layers, we see other patterns. For instance, here we see patterns related to food, another hot topic in Instagram. Or in this other layer, we see patterns related to Football Club Barcelona, which is another hot topic in Instagram related to Barcelona. Okay, so that was all for the second chapter. Okay, going with the third chapter now. In this chapter, we are going to deal with image text and an additional modality, which is geolocation. And this is the three research questions we are going to answer. The first one is which one is the best method to learn with images from images with associated tags. So no locations used here. The sixth one is about how can we exploit jointly visual information and location information to improve image tagging performance. And the seventh, it's about how can we train a retrieval system to retrieve images related to a given tag and near to a given location. And we are going to see in this chapter which challenges using this additional location information comes with. So yeah, this is the first tag, location-sensitive image retrieval. So in here, for instance, we want to train a model to retrieve images related but associated with a location. So for instance, we want to distinguish between temple images Athens and temple images. The second tag, location-sensitive image tagging, we want to jointly exploit visual information and location information for image tagging. So for instance, if we have this image of a generic mountain, let's say, and we know that it's located in Kathmandu in Nepal, it will be easier to predict the tag Himalayas. While if we know it's located in Berna, it would be easier to predict the tag Alps or Switzerland. So in this chapter we work with this dataset consisting, it's a large scale dataset consisting on 100 million images of Flickr with associated tags and geolocations. We are going to work with a large vocabulary of 100,000 tags and with locations represented as latitude and longitude normalized between 0 and 1. So this is the first step of our method. We are going to learn visual representation using the hashtags as supervision, right? And we are going to benchmark three different baselines to do that. The first one is multi-class classification, where we use a softmax activation and a cross-entropy loss. For the softmax activation, at each training iteration, we are going to select one random tag of the image in case it contains more than one, which is typical as the positive one. The second setup, multi-level classification, which set each tag as an independent classification problem with a sigmoid activation and a cross-entropy loss. And the third one, which is similar to the one I was using in the second chapter, it's a hashtag embedding regression, where we are going to train a net to regress its associated tag globe embedding. So results on location agnostic image retrieval and image tagging show that in both tags the multi-class classification method is the one performing best, with a huge difference actually. And that might seem counterintuitive because we have multiple tags per image, but it's consistent with results shown in other works, are the one I'm citing here, when we have a large number of tags. So once we have trained these visual representations, we are going to train the Loxes models. The Loxes model has as inputs triplets consisting on an image, a tag, and a location, which is here. It's hidden, but it's here. And remember, the location are coordinate, latitude, and longitude coordinates normalized between 0 and 1. And we are using pre-trained image and tag representations. So this model, it's going to map the three modalities to the same dimensionality. It's going to normalize them, concatenate them, and then we add a set of fully connected layers until we predict a triplet score. And we are going to train the model to score positive triplets, which exist in the dataset, higher than negative triplets, which we create. And we are going to train it with a ranking loss. So when we trained this model, we found out a problem, which is that basically the model was using location too much. It was relying too hardly on locations to rank triplets. So for instance, when we were retrieving images associated to a tag and near to a location, it was retrieving images always near to that location, but maybe not that associated with the tag. So we proposed two strategies to solve that. The first one, progressive fusion with location dropout. In here, what we do is, at the beginning of the training, we multiply the location representation by 0, and we introduce that modality progressively during training. So we keep scaling up this multiplying factor until it's 1. And we also apply a dropout here, so that the location information is not always available during training, so that the Loxen's model still can discriminate between triplets based solely on image and tag information. The second strategy is location Gaussian sampling, where during training we are going to sample location from a 2D Gaussian distribution centered on the ground truth latitude and longitude, and with a variance that decreases during training. So at the beginning of the training, the variance will be very huge, will be 1, so the location will be not informative at all. But during the training, we reduce that variance, so the location starts being more informative. And that method also allows us to train models sensitive to different location granularities, because the variance of the Gaussian has a direct geographical distance interpretation. So those are some results, some location-sensitive image tagging, image retrieval, results. So we see that the model distinguishes between different temporal images along the world, and it can also distinguish between concepts that are not so typical in the location. So for instance, it can distinguish between winter images in Berlin or in Chicago. Here we have some challenging results, where the query concepts does not exist in the query location. So for instance, if we retrieve beach images near Auckland, we get beach images from there. But if we try to retrieve beach images from Moscow, where there's not a beach nearby, we are going to retrieve images of people sunbathing, which is kind of semantically similar, right? And the same if we try to retrieve ski images from Sydney, where you cannot ski, we are going to get like surf images, which is also kind of similar, right? To evaluate the location-sensitive image retrieval, what we do is consider images correct if they contain the query tag and they are near to the query location than a given threshold. And we evaluate the models at different location thresholds. So what we see here is that when we input the raw locations to the model, these models perform very good at fine-grained locations, but at expenses of a big drop on location-agnostic retrieval. And the proposed location balancing techniques allow us to train models with a better balance between retrieving images related to the query tag and near to the given location. Those are tagging results. And in here we see that the model only analyzes visual and location information to predict tags. So for instance, in here we have this image, which we know is in London. And while a location agnostic model is predicting New York, San Francisco, Skyline as tags, the Loxen's model is predicting Thames, London, Docklands, Skyline, right? So it's jointly interpreting both modalities to predict better contextualized tags. Or in this other example of a church image in Paris, a location agnostic model is predicting general tags such as church, cathedral, tower, London, while the Loxen's model predicts architecture, church, Paris, Église, or even Montmartre, right? So it predicts more informative and specific tags. In here we have results of an image with different fake locations. So for instance, if we have this sailing image and we know it's in Cuba, the model is going to predict tags such as ship, catamaran, ocean, Caribbean. But if the image is in Toronto, where you don't have an ocean or a sea nearby, it's going to predict lake, right? Or if it's in Barcelona, it's going to predict sea, velero, mar, Mallorca. This evaluation of the location-sensitive image tagging. So we see that the log-sense model outperformed the location-agnostic models in both accuracy and also in diversity, right? It predicts more diverse tags, and therefore more informative tags. Okay, so some observations of this chapter is that the proposed model manages to perform both tags exploiting both modalities. And also we have identified this problem, which is that it relies too much on location for the triplet ranking. And we will have proposed 2 strategies to overcome that problem. In general, training networks that deal with different data modalities, it's a very challenging task. And there are recent works, like the 2 ones I'm citing here, which study how to deal with these modalities in similar ways as we have proposed in this work. Which, by the way, all this chapter was published this year in an ECCB paper. Okay, so going with the 4th and last chapter of this thesis. This is about multimodal hate speech detection, which is basically trying to identify hate speech in publications formed by a text and an image. So unfortunately, on social media, we have publications as this one, where if you analyze jointly the image and the text, they result to be hate speech, right? So we are going to see if we can train models to jointly analyze both data modalities and detect hate speech. What is hate speech? There are many different definitions for it, but in here, to get a fast understanding of it, we can enclose it in these terms here. Hate speech can be racism, can be sexism, can be homophobia, or can be religious-based hate. In publications formed by text and image, sometimes analyzing together both modalities is required to detect their hate speech, right? So you have to jointly interpret both the text and the image to detect their hate speech. So what we do in this work, it's we gather tweets consisting on a text and an image containing keywords that are susceptible to contain hate, and we'll label them using Amazon Mechanical Turk. So we are going to ask 3 workers to label each tweet in one of these 6 categories: not hate, racist, sexist, homophobic, religion-based, or other hate. And we are going to create this data set, right? We have 150,000 tweets formed by image and text. We also extract the image text in case there is one with the OCR, and we make this data set public. And we conduct some experiments with different models. This is the most simple model we try here. So we represent the image with a CNN. We also extract the image text and represent the image text and also the tweet text with an LSTM. We concatenate the representations of the 3, let's say, inputs. And we add a set of fully connected layers until we get a score, and we train everything for hate, not hate classification. This is a more complex model we try out. It's inspired in visual question answering works. And in here, what we propose is to learn kernels for the CNN dependent on textual representations, with the idea of giving the model explicit capacity to model textual and visual interactions. And we also train it for hate, not hate classification. So those are the results we get. And despite the image modality is shown to be useful for hate speech classification, in here we have the top score for hate images, and in here the images with higher score for not hate. The multimodal models, the ones using the 2 data modalities, image and text, cannot outperform unimodal models that only analyze text. And a reason for that is that the task is very challenging. The complexity of the multimodal relations we have to learn is very high, and they are very diverse as well. And probably we have a small set of multimodal hate speech examples overall. So how can we address these problems? Well, we can try to transfer knowledge from other tasks. For instance, we could try to pre-learn these features from other data that are useful for this task. Or we could try to learn from social media interactions. In any case, it's a topic which is a very, very high social, political, and research interest. And actually, since this paper that was published this year in Winter Conference, and we published the data set, it has got many interest, and some other works have been published in the same direction. Actually, just like a few months ago, Facebook opened a challenge about multimodal hate speech detection based on synthetic data. Okay, so that's all for my thesis content presentation. Now I wanted to conclude this defense, saying that during this PhD, these nearly 4 years, I've been able to work in many different tasks involving visual and textile data. I've been able to learn a lot and to see how the research has like real impact, and it has been a very grateful experience. Also, since it was an industrial PhD in EURECAD, I've been able to work in other projects related to my research. Here we have 2 examples. In here we train a fully convolutional network for face and hair segmentation for a private project in EURECAD. And in here we work on an aerial robot that's a drone for sewer inspection. It had a camera taking images of the sewers, and we train also an FCN to detect automatically scratches in the sewer, which also resulted in a publication. I also had the opportunity to collaborate with other researchers. For instance, in my stay in the University of Trento this year, I was working with Yahui Liu, a PhD student there, and he was working in image-to-image translation. So we combine our knowledges, my knowledge on image retrieval and his experience in image-to-image translation, to use an image retrieval system to boost the performance of an image-to-image translation model. And from that project also a publication came out recently in ACM Multimedia. So also a pleasure working with you, Yahui. And now I'm continue working in research, and I'm currently in Dublin working with Huawei in video action recognition. And that's all. Thank you. Diane, hello? Can you turn, hello? Yeah, we can hear you now. Diane, can you turn the video on, please, Diane? Okay, perfect. Yeah, we can see you now. Yeah, can you hear her? Yeah. Can
you start asking Diane, please? So I can hear you very well.
Okay, you can hear me, but can you listen? You cannot hear the tribunal. Okay, it's not a big deal then. They are asking you if you can start with the questions, right?
Okay, that's a good idea.
Okay, perfect.
Okay, so first of all, I would like to thank you very much for the invitation. I'm very happy to be here for this PhD defense. And I would like to congratulate you for this very clear presentation, which covered all the contributions. It was a very nice overview, very clear. And I also really enjoyed reading the manuscript that I found to be a collection of very solid scientific contributions. And what I highly appreciated was that everything forms a very coherent line of research. There's many contributions, to say the least. And I'd like to highlight that these are really economics of the world. So that I highly appreciate it. And I have quite a few questions about this manuscript and the presentation that highly triggered my interest. And if that's okay, I will simply go linearly across the chapters.
Okay, perfect.
So first, I'd like to start with chapter 3 and or the first part of the presentation. And so you presented this very nice approach, text FCM, that you use for multiple tasks. And the last task you consider is how to use it for data augmentation. And you show experiments for the task of text detection in the wild. And this is used to produce other data augmentation. And I was wondering if you compared or if you have insight on how this data augmentation technique that has been designed specifically for syntax compares to another data augmentation technique that is only done for object detection, for example, where you have more standard activation at the pixel level or other image manipulations.
Okay, no, we have combined this data augmentation technique we propose with simple geometrical and usual data augmentation techniques, which are also included in the experimentation, such as cropping, mirroring, etc., but not with more complex data augmentation methods for object recognition that has been proposed, as for instance creating data with GANs.
Okay, so if we leave GANs aside, do you have an intuition on the kind of augmentation brought by the style modification, and if this is really crucial?
Okay, I think that it really depends on the data set you are using it for and the context you want to apply that model to. Because, for instance, here, first you are only modifying the style of the text, so you are not modifying the text transcription, right? So, for instance, if your problem on low diversity is that you have like a small amount of different words, or even maybe your problem of diversity is the context. Maybe the text is appearing always surrounded by the same context, and therefore this technique is not useful. But if you have in your dataset, you don't have in your dataset sufficient style diversity, this will be a more useful data augmentation technique.
Okay, that's interesting. So you wanted to show, okay.
Yeah.
Yes, for this particular experiment, to compare with multiple styles, but not with other types of augmentation. Mm-hmm. But the gains are really consistent, so I find that very interesting. I'd like to move to chapter 4 in the second part of your presentation.
Okay.
And I guess my first question related to this chapter is about the way you join evidence. So typically, many of the papers that's exactly what you said. Mm-hmm. So many of the papers building join image and text evidence for different vision and language tasks. Very often, they jointly learn the visual and the text embedding. Mm-hmm. And these two embedding functions, so the phi that you define for the images and psi for the images and phi for text, are hand in hand and really helping each other. And for this model that you use, you've used a slightly different approach where you do this sequentially trusting the textual embedding to be the final representation space and training the image representation to live in that same text embedding space. So can you comment on this design choice? If you think it has a huge impact on the result, or is it really like just some details of the implementation?
Yes.
And, do you think there are cases where one approach is better than the other?
Mm-hmm. Yes. So yeah, this is a design choice. Actually, you can do it effectively, training both the visual and the textual embeddings, and you can even train them at once, train them together. But with the choice we take here, which is basically learning to embed images in the pre-learned text embedding space, we are first taking advantage of the pre-learned text representations and of their semantic structure. So we have the joint embedding space fixed pre-hand, right? So we already know to which space we are going to learn to embed those images. If you don't fix the space, you have more capacity in your model to learn the optimal space for the task you are optimizing for. But the resulting space will be, for instance, less interpretable and less controlled, right? So, of course, for different tasks, the other choice may be more suitable. But for this one, we wanted to take advantage of this pre-learned space, fixed space, to ensure its semantic structure. And also, an additional benefit you could get from it is that you can pre-train that text embedding space with additional unannotated training textual data, and take advantage of that pre-training on your overall model.
Okay, that's a very good answer. And I have a follow-up question still for this slide. For this joint embedding, we use the cross-entropy loss to train.
Yes.
And that's a very reasonable choice, and it builds very good embeddings. And I was wondering what other losses could have been used. So in the manuscript, right after we discuss about the mean square error loss, and a bit later in the manuscript for other tasks, which have, I would argue, fairly similar models, you also consider ranking losses for these other tasks a bit later. So yeah, can you comment on the choice of the loss and when you think it's appropriate to use this kind of cross-entropy loss or ranking losses?
Sure. So actually, in this model, in this chapter, we experiment with cross-entropy loss, but also with mean square error and ranking loss, despite the results are not included here or in the paper, because we got worse results with them. So with cross-entropy loss, we are treating each dimensionality of the embedding independently. And the minimum loss of our problem won't be zero. The optimum loss for our problem won't be zero, but it still it turned out to result in a better representation for image by text retrieval. Ranking mean square error loss could be used equally for regression in the same pipeline we were using here, but using the mean square error loss. Regarding ranking losses, which also resulted in good results and are widely used in the field, of course, then you have to use a negative caption. So you have more flexibility there because you can use a negative caption, which is a caption associated to another image, or you can build them yourself. You can investigate on using hard negatives. We got some results, but the training seemed pretty unstable, meaning that with cross-entropy loss, we were always getting consistent good results, while with ranking loss, results were not always good. And as you said, in this second, in this second part of this chapter, we do use ranking losses. In here, there's a difference with the previous pipeline, which maybe I have not explained in detail, which is that instead of directly embedding images in the Word2Vec space, from the Word2Vec representations of the captions, we compute a neighborhood context. Neighborhood context is basically a vector which has one dimension for each one of the neighborhoods in Barcelona, containing the similarity of the words in the caption with that neighborhood. So here the setup is different because we are actually not directly embedding images in the Word2Vec space, but in this new created space which we call neighborhood context. And in this setup, ranking loss ended up having better results than cross-entropy loss.
Okay, and I was curious about a detail about this second part of chapter 4. So you have this very interesting study where you look at multiple models with multiple languages, and you to look at these different views of the data, or at least at neighborhoods.
Yeah.
And I was wondering if there's any part that is shared between the three languages, or if they are purely independent models that you've trained for each.
They are totally independent models. Both the Word2Vec, like I trained one Word2Vec model with each one of the languages, and also one CNN for each one of the languages. Because of course, for different languages, you are also going to learn different representations for the words with Word2Vec.
And there's nothing on the visual side that is shared between the languages. So you train visual representation.
Yes, only an ImageNet pre-training is shared.
Okay. Okay, well this application is very interesting. If we have time, we can probably go back to that for a higher level question. But
Okay.
I'd like to move to chapter 5.
Okay.
And it's very part of your presentation. And you've discussed about choosing the sample was critical for the ranking loss for the second part of chapter 4. And for the chapter 5, you have this model where you have triplets, and you build positive triplets and negative triplets. And you mentioned several ways to build these negative triplets. And I was wondering if any of these strategies was more successful than others, or well, if the way you build this triplet has a strong impact on the result, and if certain types of triplets were more benefic to the training.
Yes, so I experimented with different ways of building triplets. And actually, yeah, it has an impact on the results, and the impact is different for the tagging and the retrieval task. So for the image retrieval task, we are building negative triplets, changing one of the elements as it's explained here. But for the tagging task, we get better results, actually much better results, by generating triplets by only changing the image. Why is that? Because in the data set, different tags have very different frequencies. So there are tags that are very common, and there are tags that are not common at all. So if during training you also change the tag of the negative sample randomly, you are going to train the model to understand that some tags are always present in positive, are more frequently present, in positive triplets than in negative triplets, right? So the model is going to not be trained properly because it's going to learn that those tags are always the positive samples. While if you don't swap the tags, you are going to keep the same tag frequency in positive triplets and the negative triplets. So that is going to result then in a more realistic tagging results.
Okay.
So actually, despite the architecture of the model, it's the same. The trained models we use for the tagging and the retrieval results are different because they have trained with this different strategy on triplet selection.
So did you observe that it was producing better models, or it was converging faster, or what kind of different behaviors did you observe?
It was producing better models. It was training models that get at least models that get a better tagging results in this dataset. Because of course the triplet selections are going to be involved on the resulting tags, and if you want to get the higher score for this specific dataset, for this specific ground truth, this was the best negative selection strategy. But maybe you are interested in predicting other tags that don't share the same frequency as the ground truth do of this dataset, so maybe you could also play with that for getting different results.
Okay. Okay, very clear answer. To continue with this task, so the way the model is designed is that it computes compatibility scores for triplets. So this means that the compatibility score is of course different depending on your query. So can you comment on how much can be pre-computed for this task, and how much needs to be computed on the fly when a query comes, and if this has an impact on the computational cost, and if you see ways to reduce that, or if you'd like to comment on it.
Yes. So in this model, the image and tags embeddings are pre-compute, but during inference, you need to compute the triplet. For instance, in image retrieval, where you want to retrieve images close to a tag and near to a location, you have to compute the score of that tag and that location with all the images on your retrieval set. So that's not very efficient because you have to run the model for each one of those images, right? Despite you can do it in batches. And for tagging, it's the same. For tagging, you have to compute the score of images and locations with all the tags in your vocabulary. And that's not very efficient either. So a solution, actually we started working to solve this, is to instead train the model to compute triplet scores, train the model to compute embeddings for image and tags. For instance, for retrieval, to compute embeddings for tags and locations and with images, right? So you can pre-compute the embeddings for the queries, for the multimodal queries you are going to have, and all the images in your retrieval set, and that an inferring testing time, you only need to compute distances between those embeddings. This has the drawback, let's say, that you would need different architecture for testing, for tagging and retrieval, but still it would be much better because it will be much efficient during testing time. Though the experimentation we did with these architectures was not successful.
Okay. Okay. Thank you. Can we move to the last chapter, or last introduction chapter in the last presentation? And I'm curious about this task that when we started exploring it, it was not it was still a not very studied topic, and as you explained, now it's gaining interest in the community. And while starting this research direction, you did this very challenging task of gathering a data set. So you had to find publications, and you had to ask the annotators to annotate them. And I was curious how difficult it is to annotate this publication, and how much annotators, in your case these were Amazon Medium interpreters, right? How much they agree on the annotations. Yeah, because you have 3 annotations for
Yep.
publication, if I remember correctly. And yeah, that was
Yep.
one.
So as you say, this was a very challenging task. And actually, when I started working in this project, we were supposed to have a social partner, let's say, because this project was we started working on it because we have a consortium with Eureka to work with a social partner. So basically, we were going to take part of the technical part, while we are going to have a team of another institution where experts on hate speech from the social point of view, we're going to take care of dealing with all these annotation procedure. But we lost that social partnership, let's say, and we continued working on this on our own. So yeah, we had to read a lot of papers, a lot of research, a lot of analysis on hate speech from the social point of view before working on this, before creating the data set. And finally, we decided to, in a very simple way, show the Amazon targets annotators just a very simple hate speech definition as the one we have here. And show them different tweets together with images to directly annotate them, just reading this definition and with their concept they have of hate speech, right? So yeah, then the annotation procedure actually was quite challenging, difficult, and we got a lot of feedback from annotators. Some of them asking questions about how they should do the annotation, others maybe complaining, saying that that task was not very objective. So different kinds of feedback, and we actually learned a lot from that feedback. So yeah, finally, as you said, we annotate each tweet with 3 workers. And so we can do a majority voting between these annotations, right, to get the final class for each tweet. And we also investigate basically treating this as a regression problem, where, for instance, the tweet that has been voted as hate by the 3 workers had a solid, more stronger hate score, while the intermediate ones, the ones that had received 2 or 1 votes for hate, had a softer hate score. And we did that actually because the agreement between annotators was not really big. Yeah, so we did some experiments with that. Also some experiments treating this as a as a multi-class classification problem between these different hate class. And we have results for that, but we decided to keep this work and this publication as a simple study presenting the dataset and presenting the simple models for the plain binary hate, non-hate classification task. Also, because training these multi-class or regression models, we didn't get further improvements in the scores neither.
Okay, a very challenging task. And,
yeah.
Yeah, great step towards like facing this.
Yeah.
Problem. And I have I took a lot of time already. In fact, I can already finish with one open question, very general, and I'm not sure there's a right answer to that, but after all these chapters that you've covered, where you've looked at these image and language models, I want to have your take on something related to the bias in the datasets, because there's a lot of discussion at the moment about the bias the dataset capture and how the models capture them, and there's a few things in the manuscript that are really interesting. Like, for example, when you're showing qualitative results for this semantic retrieval class, where you have the keyword snow and that particularly out of snow leopard, one of the figures you have in the manuscript. I don't think it was in the slides. And also you show in the next chapter how different images and different tags are used by people of different community, locals versus tourists, for different neighborhoods. And you look at some bias that is captured through different angles. And I was wondering if you think these multi-models that have image and text together are good tools to start analyzing the bias in a more interpretive manner that is not always possible for the purely visual models. And if you think this kind of tools can be used to do this analysis of bias in data sets and models. I know it's a very open question, a pretty challenging one.
Okay.
Looking at all the insights in the manuscript, I thought we could start discussing this
Okay.
subject.
Yeah, so I see that when dealing with this multimodal social media data, of course, you are learning a lot of biases, and you can do that from a social study point of view by basically which kind of concepts, visual and textual concepts, people from different communities, from different places associate. Right, and I think that's a very interesting application for that. Regarding using these multimodal associations to deal with dataset biases, I'm not sure what you mean here, because basically you have you have bias in both kinds of data, and you have bias both in associations, right? So in social media data, in different communities, or in data from different social networks or from different times, you are going to get different distributions both in images and text, that they will evolve over time, and also the relations between images and text will change, right? So I'm not sure if I got your question properly, sorry.
Well, it was a very open question first, and
Okay.
yeah, I think you already gave some very
Okay.
good points in your answer. I still cannot hear the president of the jury, but I guess I will stop for now. I already asked quite a lot of questions, so I'm going to leave the floor to somebody else.
Okay.
Thank you very much for all these answers.
Okay, thank you.
Well, Raúl, first of all, I would like to congratulate you for the work. I really enjoyed the content, also the manuscript, the presentation, and also the presentation. So it's a very good piece of work with many contributions. And there is one thing that I would like to highlight. And when I was reading your dissertation and also the presentation, I noticed that it's brilliant. You propose each chapter, has an innovative idea from a point of view of maybe a new application, a new service, something related to social media and something like that. That's right. The methodological contributions of that. So I think this is what is expected from a PhD. It's very like it's going to work. No? So, well, I have some questions. Most of my questions are just in that direction. No? Working on the really innovative way of developing the world, and probably the new challenges that you are offering. I am also raising some potential ideas in the future. Let me follow also the order. Start by contribution, chapter 3. For chapter 3, you mentioned it, no? It's your first contribution, the work you did from years ago, and of course at that time it was probably something that detection in general, in the wild, something that was really new. Probably now, when you see the rest of your work, you propose new contributions that improve the state of the art that you made at the beginning. No? So, probably most of the questions do not make sense because I read in the improvement that you do afterwards or the line, but in any case, I guess you take it. Concerning the style transfer method, what you are applying techniques that basically work on the, let's say, the photometric style. So you are basically transforming colors, general geometric transformations of the image, formation, that make the appearance of the new image, of the new text, of the transforming text image, similar to the I was wondering about the properties that the different text fonts have and actually characterize the style. So, for example, there are fonts that are with or without serif, fonts that are monospace or non-monospace. So these kind of properties probably are not really captured in the same. Do you think that it's possible? It's probably something that is very detailed, no? But do you think that it's possible to improve somehow this kind of features that characterize a particular form?
Yeah, I think that, for instance, you could model each one of the text style properties you are interested on separately, for instance, right? Maybe with the same model, but model them separately, so that then you can basically choose which one of the properties you want to apply to the new text, right? Probably you can, let's say, discretize the text style, right? If it's serif or not, if it's bold or not, which one is the color, which one is the shape, which one is the width of the strokes, and by discretizing that, learned better style transfer models to play with all these features. Yeah. At the end, also, of course, you could use other kind of methods to do a style transfer as GANs, for instance. They are also used for this. But even using this kind of pipeline, here you are playing, right, with low, mid, and high-level features. So and this is an ImageNet pre-trained network. So at the end here, we are assuming that these high-level features are going to encode the text transcriptions, but and that here these low and mid-level features are going to encode the style, right? But even using this pipeline, you could play with this. You could, for instance, here weight the amount of a style you want to copy to the next image. You can reconsider the layers you are using to apply this style. Even the method we use here, that's not in the presentation, it's in the paper, allows to interpolate between styles. So basically, you can transfer a style by mixing up the two different styles here, mixing up the low and mid-level features of two different source styles. So even with this pipeline, this allows further research on doing a more controlled, let's say, style transfer.
You formulate the problem as, for example, the text replacement. So instead of directly applying the style in the image, the text in the text, and then for this, probably the request is another, but style on separate image and then replace it and then putting the image with another alignment.
Yeah. Yeah, it makes a lot of sense, I guess, because you could also control better how the style is transferred, right? Since you can control how those images where you apply your style are, and then paste them back here. Yeah, I think so. Though then you see some results. And you see that sometimes the integration itself of the style in the image is quite good. So probably here the net it's also learning how to put this text here, right? Preserving the context. But for sure this is very open and unbounded, right? We are learning to stylize the whole image and then applying style here. So for sure, working under more controlled under a more controlled scenario, we could probably obtain better results. Yeah.
Okay, let me move to the second application. Okay, well, so you have in my question that there is on this. I want to reformulate it in you are basically embedding the text, the format, or right, or whatever, and then you are forcing, aligning the learning, the transformation that you have to apply to the image to generate this image. No? So it means that basically what you are capturing is in the text embedding methodology that you use, you are capturing the relation between the words. The relation, semantic relation, or just the co-occurrence of the words when they are using the text. So you are forcing that the image is aligned with the relations that the word has in a textual appearance. My question is, what about doing the other way around? So there are visual relations between the objects that also define the context in the case of the visual context. And probably you are losing this information. You are using the semantics of the relation in the textual part, and then you are transferring it to the imagine do the model is the other way around. You force the textual embedding to be aligned with a potential image embedding based on detection of objects, relations between objects.
Yeah, so in this case, you would be basically learning embeddings for words in a space which will be structured based on visual similarity, right? Because if you train a CNN, then images that are visually similar are going to be embedded nearby, and the same for text.
I not just similarity of images, but relations between parts of the image, so that the objects that appear, for example, in one of the examples you showed, you say that when you have component queries, one of the queries that you mentioned that does not work is, I remember, a fish and a dog. Well, probably there are many images that contain fish and dogs. No, if we were able to represent somehow fish and dogs in a visual representation with the corresponding embedding and so on, then probably the words in the textual embedding would really use the regular results in that case.
Okay, so you mean represent different visual concepts in an image separately, right? So that we can associate them with words.
Yes.
Yeah, how would we design it? Yeah.
We use the idea of embedding items
Mhm.
or in that case and their relation to live in the visual space.
Mhm.
And then the other part, the textual part,
Okay.
the visual language.
Okay.
So we are
Yeah.
generating a new workflow based on the visual relation.
Yeah. Yeah, that would make sense. Actually, we have discussed similar things because this pipeline here has some limitations. For instance, for certain images, maybe they are embedded in two very different points in here, right? So if you have this space, maybe an image has some visual similarity, source semantic similarity with a word that is around here, and also also semantic similarity with another word which is around here, right? As the example you were saying, right? You have kit, here the word kit, and here you have the word dog, right? So probably you are embedding this image, let's say here or in any. So yeah, regarding this idea, we thought we have spoken sometimes about, instead of learning an embedding, a single embedding of an image in this space, learn a distribution. Like for instance, a probability distribution of images over this two-vec space, so that then you can have a more where images have relations with the different words. So different words, right? So that would you flexibility and would let you learn more complex image and text relations.
Okay. Let me continue with this presentation.
Mhm.
So I think it's very, very interesting the idea of the arithmetic operation, the idea of making complex combining queries and then addition, subtraction, and multiplication. I really like this idea. So another example you showed, for example, was fast food. No?
Mhm.
And then fast food, probably the embedding, the word embedding, two words that probably come together very often, and then they say you have them grow, of course, does it mean that, so for example, the two words when they are projected and they are added are words that are close in the space?
In this specific case, they might be a bit close because we have also trained the text, and probably since here together. So probably they are not so far away in this space. That's true, though, of course, the word food will be to sandwich than healthy, right? It's not that the two words point to the same point in the space, of course. Another thing we experimented with, and you can do, is to when you combine these representations, you can weight them, right? So for instance, you could query with food, you get generic food images, and then you start summing up fast with some weight. So when you start summing up fast with small weights, or let's say 0.5, you would get those images. But if fast now is weight with 0.8 or 1, you would get here, I don't know, images of fast cars or something like that. There's an interesting example. It's included in the manuscript. We have the word train, which has two different acceptions, right, or meanings. It can be a train, like the vehicle to travel, or it can be a train in a gym, a sport thing. So basically, when we retrieve images for a train plus car, let's say, we are going to retrieve these train vehicle images, and then if we slow down this car weight, we are going to get training images in the gym. So basically, by weighting that, you are navigating this space as well.
So my next question was somehow related to this, no? If you have analyzed the processes in this space that allow you to make this, not really way also. For example, another case. Imagine that your body is food plus food, so twice food. Does it mean that twice food is like waiting for images with a lot of food? And if you have five times food, means that the plenty food. So in this arithmetic analysis of the space, we could construct a kind of polynomial query expressions that way means a lot of
I haven't tried that with the same words, but at the end, I think you would get the same, right? Because in here, you are pointing. Well, it depends in the distance you use actually during training. But it's different, right? If you sum up 2 dog words and 1 park word, you are basically biasing your results toward dogs. But if you sum up 2 dog words, I'm not sure you are asking for more dogs in the image. I don't think so. I don't think so, because you are pointing to one place here to the representation of dog. But if you double that, no, I'm not sure you would get more amount of that semantic concept in the image.
Okay, so let's go to the next one. For the geolocalization of waves.
Mm-hmm. Is the method Scala, you are entering that query in terms of the geographic location. But for example, if you add a new criteria, like for example, could be type video. So I'm searching for beaches in Barcelona, in Nancy. You could do it. And actually here in this work, we are this could be swap or could be added. Of course, that would come with additional challenges, as the challenges we have since here dealing with locations. Actually, this work is inspired by a previous paper where what they actually do is train a user-sensitive, let's call it like that, tagging engine, right? Using social media, they train a tagging engine to produce different tags for different users. It's something, the idea is similar, right? If a user always posts images related to I don't know, mountain, right? His tags are going to bias it towards mountain in the Alps, let's say, if he's from there. So in here, they use that other modality, which is like actually a user ID, right? So of course, it can be applied to other modalities as time. Actually, time would be a very interesting one, because it's also a real case you would be interested on, right? On retrieving images in a given time. And actually, we also discussed that with Luis and Dimos as well. I remember that, because this can have a high interest in historical data, right? For instance, to classify or tag images of old, ancient art pieces, or anything like that.
Yes,
Yeah.
I was just speaking on this because in the sense that you show inconsistencies when you ask for pieces and then the location is right in a mountain.
Mhm.
So then, of course, inconsistent the two values. Okay, it happens the same with the time. So if you ask for skyscraper from New York 2 centuries ago,
Mhm.
probably there's no sense. If that is the problem, and probably you can figure out the problem and do this for taking from 30,000 photos.
Yeah.
Somehow, depending on the object, you can find location even, you can infer that it should be this period or this point.
Yeah, yeah, of course, that's interesting. Here at the end, what you are learning is location-dependent image representation. So a temple looks different in Greece than in here, right? Or a mountain, right? And you could also learn time-dependent image representations. Yeah, of course, like you could learn how buildings look like 100 years ago and how they look here. Yeah. Yep.
Also, temples look different depending on the text.
Well, yeah. Of course, of course, of course. Yeah, yeah, yeah.
Depending on the text,
Yeah. Yeah, 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 yeah.
okay. I think to with the last chapter, the hate speech situation. Also, in hate speech, some offensive words that appear on tweets or whatever, are more offensive depending on which culture or which places were generated. No? There are words that for someone is a really bad word, and for some other one is a colloquial word. So why not combine with the various words if you're localizing
Yeah.
the hate speech effect?
Yeah, that would be an interesting thing, and that's also, I think, related with the thing Diane mentioned about biases in social media modalities. So yeah, of course, you could do that, and it would be very interesting. I didn't mention that, but in here we were asking the workers to be at least located in the U.S. To ensure they knew the slang and all the vocabulary, because they use a lot of the slang in social media, and specifically in hate tweets, right? Actually, when we were working with this data, I was learning a lot of slang and yeah, words I didn't know related to this and their different uses and why they are offensive or not. So yeah, sometimes and the image associated to the tweet can be useful to know if that tweet is hate speech, but yeah, also knowing more context about the situation, like when that post is tweet or who is the user who posts that, can also give you additional information, of course.
Okay, yeah, last question. In this work, you have like three components. No? You have the text, you have the text that uses the image, and finally the image. I have the impression that text speech to the text that the most important thing is the text. Both. The textual, the written text or the text that is not images. But how we do it, I don't know if you have studied the importance of this component. How important is what visual value? Just the image, without considering the text.
Yeah, so The thing is, yeah, in general, the text is more informative, and also the image is more difficult to interpret for both us, because generally we need context to understand images, memes for instance, and even more for an algorithm, right, that does not have all the background information we have. So in general, yeah, text is much more informative. Actually, in the results here, I was training the different models with different inputs available. So in these input columns, TT means tweet text, image text means, well, IT means image text, and image, right? So in here we see the results that the models get with each one of the modalities, right? Here you can get an appreciation of that, but also one of the focus of this work is to investigate when both modalities are needed to detect text, right? When the text, well, actually, as in this example, right? When the text is not hate speech by itself, the image is not hate speech by itself, but the two modalities together, the joint context of the two modalities together make this hate speech. And actually, this is not a very a problem we made up. This is a very common case because people in social media often they are like afraid, let's say, yeah. They don't want to write a tweet that contains a lot of hate, very strong hate speech in text. They won't upload a very strong image containing hate speech. But as it happens with memes, when it's a combination of an image and a text, it's more like a funny thing, you know, it's like more, so finding hate speech like this, it's very common. I even find it in the social media. I see it really in my life, right? So it's a very interesting problem. And actually, in this challenge, in this Facebook challenge here, Facebook recently opened, they create synthetic hate speech data. They are kind of, yeah, they are like memes. Yeah, actually it's hateful memes challenge. And they, when they create the data set, they ensure that both the text and the image are important, right? Because the challenge is to train models to jointly analyze those information. Yeah, I've been, and actually, yeah, it's a very interesting challenge. And I'm aware of it because also people is contacting me because people is using also this data set because they allow to use additional data, right? So yeah, I think this challenge also will make the field even more broad. And yeah.
There is a type of images, so probably it tends to really focus on the people that are comics or caricatures. These kind of images were really when the author is drawing the object that appears there is exaggerating from just to one. So probably in that case really makes sense to detect this kind.
Yeah. Actually, here the net is detecting this bias. Sorry, right? These ones are images that are scored higher as not hate. So here it's just images of people posing, you know, like normal portraits. While here are the top score examples for hate, which are memes and this kind of caricatures. So yeah, in this kind of images, probably the image is more relevant. Yeah.
Okay, I think we'll just cover all the topics more or less, with some questions. Just like this is a last question that is more interesting. Going back to the beginning, so I said in the beginning I like this industrial component or application guided component of the work. So many of your contributions could end whatever. So what are the plans? Do you have any bamboo or your colleague? Is really something that you have shown something that
Okay.
starting point of maybe a new company or I don't know.
Yeah, not right now, let's say, but also I just finished this work, and as I told before, I'm like still working research now, but I really see a lot of potential. And when I was working on this in Eurecat, we actually collaborate with some very related works in some projects we already had active, and we actually were active on looking for new projects, new direct products of these applications, right? So examples all over the hate speech project. The European Union actually now is putting a lot of effort on this. So there are different calls open regarding hate speech. Regarding location image retrieval, we know that our partners working in tourism analysis in Eurecat are also very interested on this. Regarding the social media applications we're learning from associated text, here the tourism industry was very interested on this, though it's true that this was a very early stage research, let's say, and they wanted something they could handle. They wanted a build project on this, right, which we didn't have. But there's a lot of potential on this. Even we got interest from diverse company, which, for instance, wanted to know which visual concepts people in different parts of the world related with abstract concepts, for instance, as wild, as softness, I remember, as happy, because this has direct applications in advertising, for instance. I think now I'm not working in any industrial application of this, but I really think that from here they can come out many of them. Yeah.
Okay, thank you very much. Congratulations again.
Thanks.
All right, thank you. So, going on with further, after Diana and Jeff, I have to throw out many of the questions I already asked. But what I shared with them is that I wanted to manipulate you, the advisor flow, which is great to us. So I like a lot communicating, hopefully the independent connectivity was excellent. He clarified many of the things I was not sure about. And just I want to highlight, I particularly like chapter 5, the Loften's work is, I think, is great, it's very nice. Then the practical utility of the method, that actually it was a surprise for me, because I was not aware that this was mentioned this in the document, actually. So I read the document, and when you said that, then I understood why there is this kind of suitability of the work. All right. Then I also like some of the chapters that are especially the introduction and the chapter 2 of background are put in a very pedagogical manner. So then also the discrimination that we spoke at the forum, and also I checked the blog that you created that I wrote, and I think that's something very interesting. So usually after research many times don't do this kind of discrimination, so I also want to go. So I also like to on this part on that
Thanks.
discrimination, which is not just art. So then you have the considerable number of publications. I counted like 8 as the first author, and some of them are in sub-companies like HC and HC and Media, which considering that I'm used to PG, I think that's what I just find out that this wasn't used to be. You can comment a little bit on the experience on how this you will use most of the work at the company, or as if you can just comment a little bit on this.
Sure. I think I was very lucky because the company I was working with, Eurecat, is a technological center, which basically, well, its idea is to transfer knowledge from university to companies, right? So there we get projects of generally big and medium companies that are interested in applying latest research, latest technology in their company, right? So we are able to, and we work on doing that. And we also do our own research or applied research. So basically, yeah, we have been working all together. Physically, I've been like here once a week and there 4 times a week, but we have always been connected, and we have tried to to work on topics like those ones that have both a research interest and a commercial interest, right? Topics that are like new research that can be published and that can help like advance further the field, but that also can be applicable directly in products, right? So it has been like this. I would say that I've been able to work most of the time on research, while applying this research or related topics to projects we have had in Eurecat, and actively collaborating with Jaume and the other mates there on Eurecat. So that has been a really grateful experience for me, because while doing research, I've been in contact with industry, and I have been in first line seeing how research can be applied to industry, and I think that's a good part of it. Also to don't lose focus, right? To control that what you are researching on has a direct application, which I like.
In the chapter 1 in the introduction, so what we're using in documents, clear objective and hypothesis convolution. So you just formulated the chapter in terms of first questions, but I think that this is not a clear object. So if you like now to summarize in 3 bullet points, which do you think, so not the objective, but the main contribution of your work, what would you say?
Okay, so here basically was, as I said, but that time the pipeline of text understanding was an object proposals method and then a word classifier, right? But that time all these fully convolutional networks were coming out from object segmentation. So our contribution was to apply this to text. Our complete contribution was to apply this to text and to improve the current pipeline. It's true. And then start working on text detection, because I swapped to this with images and associated text. But let's say that we started here, and then this field of text detection, you see fully convolutional networks or convolutional networks went ahead, right? I remember one work after this one, which after this one that was directly predicting the bounding boxes with an FCN by training directly to predict the borders. And then the state of the art changed to directly predicting with a CNN the bounding box coordinates, right? But that time we had to stop working on that. Then here in the second research question, on the second part of this first chapter, our contribution was this style transfer to text, demonstrating that it's useful as a data augmentation thing, and specifically, I would say, to design this end-to-end model to perform style transfer and detection at once, right? Because until now, the style transfer networks were dealing with all the image, and I think this selective style transfer method that can stylize directly one part of the image can have many applications in object detection, for instance. The second chapter, I think here was also a very beginning of this field of what we call here self-supervised learning using supervision, or you can call it webly supervised learning because you learn from the web data, or text supervision. Even like the term people use for this field is not very clear because this self-supervision term keeps changing over time because it is and it was a very new thing. So when I started the PhD, Luis, director, had started working on this, working with Wikipedia, and they were, and he was basically learning visual features from Wikipedia for self-supervised classification, and I thought that applying that to social media would be very nice. So I think the main contribution here was to explore how we could train models using this caption as supervision, and to explore the potential this has, to explore the potential, how robust it could be in image by text retrieval, how we could exploit the semantics of the text representation models to directly embed images there, right? I was discussing with Diane, and also working on which applications this could have, right? Like in here we use this Barcelona data, but basically here I think we propose how this text supervision can be used not only to learn visual features to then compete or benchmark this method to compare with other unsupervised method or supervised method, but to find a real industrial application of this learning. Then here, I think that my main contribution, regardless that the method that performed well in these two tasks, it's basically the analysis we do here on why handling the three modalities is difficult here because we are fit to location. This is very interesting because, and also as I said in the conclusion of these chapters, these nets that have to handle with different modalities, it's a very hot topic nowadays. So here what happens is that this model or multimodal models are overfitting to this modality before generalizing to the other, right? So you have to balance modalities somehow during training to avoid that happen. In here we propose this method which we apply to locations, but as we discussed could be applied to other ones. And in these very recent works, they deal with this generalization to different modalities problem with similar strategies, but with a more broad, not so applied, let's say, point of view, right? So they study while training the overfitting to each one of the modalities, and they use it to balance the gradient during training. So, but I think this is a very strong contribution here on analyzing how, like, the challenges of dealing with these three modalities. And in here, despite maybe the results, seeing the table might not seem very good, I think it's a very strong contribution, basically because we were the first ones I can say working on that, and also opening the data set. And I think it's a very, very interesting field, and that has a lot of there's a lot of work to be done here, and there's a lot of interest there. So I'm really actually happy and proud to have worked on this, despite all the challenges it comes with regarding annotation, regarding reading about this from a social perspective, regarding writing about these topics, which is also quite complex, I would say.
So that the thesis has contributed, but I missed is here statement in the introduction, but this summary that we have now should have run off in the thesis.
Okay.
That's okay. Then in the background in chapter 2, what I'm looking also is, so you do very good review of cross-entropy laws and verify, but then in the part of the text, why don't you consider BERT or 50 easy to do more efficient text embedding?
Yeah, because basically this work is previous to that. So when we were working in the second chapter of this presentation with text, the text embedding models that actually fast text was added later to our experimentation because it came out, right? So basically these embeddings were not out there when we were conducting this experimentation, and since then I was working in different topics. I did not add them to experimentation and neither to the background, but it's true that I could have considered at least mentioning them in the background as new text representation methods that had been developed.
Actually, probably in the history paper which is 21 bit, so that's the written paper, so here you can see the derivative and mention that, then anything about not using the embedding.
Sorry?
In the history 21, so
no, but because basically here this experimentation, the location agnostic experimentation, its objective basically was to baseline this method, and this was to benchmark this method, and this is in line with this work, which is basically the work that models dependent representations for tagging and retrieval. So basically, we wanted to benchmark this method also with this data they did, and since the best method here was classification, and at the end in log sense we are not using any text representation, we didn't conduct extended experimentation with new text representation methods here. Mm-hmm.
Exactly get how this is used. So did you ever interpolate the features of the model, or what did you do exactly?
Yeah, so here basically this style transfer model we are using, it learns at once different styles, right? So you train it together with different source styles images. Only one style image per each class, and basically here you are interpolating between the parameters you have learned for each one of the style for the different styles you are training with. Yeah.
I also have the same question about using other augmentation methods, right?
Mm-hmm.
And you said that now you combine this augmentation method, the style, with the geometry one, so the typical one is the integer, probably mirroring. So do you have any idea how important is the style versus the for geometric augmentation method?
No, I didn't benchmark that, but basically here we were using this each text detector, right? That has its let's say default tested effective basic data augmentation methods. So we wanted to see how our augmentation improves that state of the art, right? Because maybe, I mean, if we include this augmentation, but we don't do the basic one, it wouldn't be a fair comparison, because if with basic methods you can get the same diversity and the same results as with this one, it's not. But I don't have a direct comparison of the benefit without that, right? We could, that would be having an additional line here showing how how are the results without this basic data augmentation. Yeah.
Not even clear today what is understood by this. But, well, in my case, what I think is self-supervision, I think it requires some automatic annotation. So here you even use automatic annotation. The improvements that you use are all done by humans, right? So there is no an automatic method that creates new features and labels and blah, blah, blah.
Mm-hmm.
So what do you understand by self-supervision?
Okay, so at the beginning when we were working on this, we were understanding that self-supervision, it's basically using the data to supervise itself, right? So for instance, there are many methods using different types, like when you have an image or a video, you swap the order of the frames and you learn from that, you learn the order. When you learn from different image patches, right? So in here, since we were understanding our data as a whole, images with text, we were understanding that the data was self-supervising itself, because you are using data that you found out there without additional annotations, because this was social media data, to supervise itself. But it's true that then I have found other people, other communities that only use self-supervision to refer to supervision from the same data modality, as you were saying now, I think. So yeah, I'm not really worried about the meaning that word can have, but yeah, maybe we can differentiate this by calling it web supervision, webly supervised, that's another term that has been used. Weakly supervised, because this can be considered annotations, weak annotations. No, but also the problem here, or the discussion, is text, because then out there you see supervision between other modalities. For instance, in MIT, all the work done in Torralba's lab, they use audio as supervision. They have videos or images with associated audio, and they are going to, they use that modality as supervision to learn visual features, and they call it self-supervision somehow. So with text would be something different. It's true that the problem here is that text is very related to labels, right? Because labels tend to have a textual representation. So our Wikipedia article supervision, our caption supervision, our hashtag supervision. So I think that the frontier there is not very clear. Yeah. Yeah.
So what happens in this chapter 4 when you do arithmetic with words which are not related, right? So with words that do not appear together.
Yeah. So sometimes when you do arithmetics with words that are not related, or that are not typically training data, you just go to an empty point in your space, right? You just go here and got random images. This space is very sparse, meaning that you have here we were using 300 dimensions, right? So at the end, you have a lot of distance, a lot of empty places between representations. So that's what typically happens when you do, when you basically try to get images from two concepts that are very far away. Yeah.
And everything the analysis is done in concepts which are known.
Yeah.
Do you do arithmetic with statistics or other parts of things like verbs, noun plus verb, noun plus
I might not have any result here, actually only with nouns, but you can do it with, well, actually we do have just one, you have one, right? So here, yeah, it's noun. It works pretty similar. You also have a lot of adjectives in the data. Also remember one with searching for cars of different colors. That generally works. If the adjective or any word you have, it makes sense together with the other one. Yeah.
but you do not exploit the specific part of the category, right?
No. No, I don't. Yeah.
Good. Good. Let's move to chapter 5. First, I'll go all the questions here.
Okay.
So let's move to chapter 6. Here I don't the question about the structural component of creating the data set. You answered very well to that. And also, so now I'm curious about in this kind of social media, so there are a lot of types of slang names. So how do you handle this? The type was short name, slang. So how do you handle all these?
The type of slang. Yeah.
Can be written in many different ways. Some ways are correct, others are not correct.
Yeah. We don't really. I mean, we are not use any close vocabulary, but in here in the models we use an LSTM here. But this LSTM is taking word representations, pre-learned word representations, which are GLOVE as well. And the GLOVE model has been trained on Twitter data, not with this data, but with a large-scale generic Twitter dataset. So we ensure we also have representations for words with typos or for slang or for words, specific Twitter words. And also in the encoding here of the words, we are also considering Twitter-specific symbols. Like for instance, you are considering which is a hashtag, which is not. You are considering if the word is in caps because it means you are shouting, so it's like more strong. You are considering mentions to other users, so all this stuff it's also encoded here.
And I guess also that in the text economic one that is very important with the topic that we are talking about, right? So does the data set contain some topic analysis or different topics?
No.
And what do you experience? So which are topics that express more?
So yeah, messages in social media are quite, let's say, repetitive. Not meaning always have the same data, but that they retroalimент each other, right? So if one user, let's say, post some tweet mentioning one specific situation, that to generate other related tweets. And that's also a thing that should be studied because hate speech, and I didn't mention that, evolves over time and evolves pretty fastly, because maybe now we have some situation, some, I don't know, like political decision or some event happening, and that turns out to generate new types of hate speech, or to change the existing type of hate speech, right? So if you really want to apply hate speech detection in a real scenario, of course, you should handle that. You should constantly update your model, or yeah.
Great. Just, I'm finishing the final question. One final question, a very generic question. If we had to start the thesis today, and final, and do the same topic, so they're very different. So did it change a lot what you have learned? From you started in 2016, so 4 years ago.
Yeah.
You learned that a lot of time.
Yeah. So now, with all the background and the experience I have gotten, I would change many things regarding. Of course, if I started now, I could probably contribute better, think about more clever ideas with all the experience I have, or basically, deal with my PhD differently to get more results or better results. But I think that all the research I have conducted, it has been very useful also to me to grow up and to learn as a researcher. As an example of all this chapter about learning from social media, this was very difficult to not to disseminate, but just to quantificate and to publish, right? And I spent like the whole first year of my PhD or more, maybe year and a half, working on this. But despite that, I'm still I'm still happy to have done that, because I have learned many things while doing that. Maybe, but of course I would change some things. For instance, now I would really like to work on this from a more generic point of view, because here we found this problem when we were working with this huge data set and with this very specific application, which was nice, but this data set was not very handy to investigate on this. So I would probably, for instance, start investigating in this specific issue for a more generic point of view and more handy data. But in general, I'm happy with all the research conducted. I'm also happy having been working in several topics, because maybe at the beginning of your PhD you have that pressure, like, yeah, I need to choose a topic, but I think nowadays, like, everything evolves so fast that it's okay dealing with different topics during your PhD. So yeah.
Very good. That's all from my side. I don't know if there's more Diane, do you want
Okay.
to ask anything else? No? Is there any doctor in the room that wants to pose some question? Or I don't know if we have some online questions. I'm checking the shop, we have
Okay.
and do the advisor one.
Yes, sorry, I'm beautiful. I'm from Eureka, so I wanted to say that Raúl did a great work, and in relation to your comments, I'm not sure how other companies handle this, but Eureka is a technological center, which well, its aim is to help companies develop innovative ideas. So in that sense, an industrial PhD within Eureka, I think it should be different from what it's in maybe companies that have a product that we need to develop. So when we hired Raúl, our idea was more to generate opportunities rather than solving the specific problem. So in that sense, I think Raúl did a great job. He was, as he just demonstrated, like many ideas and research problems that have applications to and more of the of trouble as a student, although he's a great student because he studies the problem and he's able to follow the class pretty well. And the other more as a work colleague, whom I have learned a lot and I have enjoyed working with. And congratulations for the work. And
Thanks, me too.
Well, I didn't speak on the name of everybody, no? But when a big machine is, you have to find whether it works and whether the student actually do something good. There are a couple of things that are not my answer. The first thing is, what have I learned in the student? Because at some point the teacher-student relationship has to switch. The student has to become the expert and the supervisor has to become a sounding board. And in this respect, I think that I've learned a lot over the last 4 years, including American fun. So, first things first, thanks a lot for everything you have taught us over the last 4 years that we've been working together. The second thing is more qualitative, no? Because there's, as a PhD student, you have to venture outside your comfort zone. You have to explore new directions and different people react in different ways. You know, people get stressed, people open loads of things that they don't close anything, and you end up doing a bit of a psychologist to deal with the student in many tools. And I think that in that respect, the way Raul is approaching things has been very, very good. Right? So he did explore lots of different things. I think that he always was comfortable. I think that was very much a goal.
Yeah.
I never managed to put him on something that he was out of his own. And he always got everything into closure. I think that he had this kind of determination to close everything closed. He never left anything open. That was a very important thing. And last thing, I think that we was mentioned that in many cases, students are motivated by publishing. They want to publish. And I think that the motivation of Raul, well, partly because of the national history, but I think it's mostly character, was to do things which are useful. And the publications are the secondary aspect of doing useful things. And I think that's a very, very important maturity element in this work. So, well, it has been a pleasure working with you, and hopefully when we see you going around the world, we'll end up here again.
Yeah, also for me, thanks.
I will add some words that very shortly to complement what you want to say with his very concise definition of the experience of working with you. It has been a pleasure. I enjoy it a lot working with you and also learning more too. It's working and there are some things that I would like to remark about what this process working with you. I think one of them is your confidence in your work and your goal determination. You are a very goal-oriented person. I share this with you, so I think it's something that makes easy the communication, this process. And I think it has been very beautiful process,
Yeah.
Years, starting not easy at all, because at some point I remember some research because it's very difficult to publish in some conferences and we tried many times, but difficult. But at the end, the results of it is equal by themselves, because they have to do it in the past. I think that really
Thanks. Okay. Okay. Perfect. Thanks. Gracias. A la mascarilla, ¿no? Molt bé. Dale.
Molt bé.
Sí. ¿Qué tal? ¿Te has enterado de mucho?